This is the Earth, the planet on which we, together with more than 7 billion people, are living and on which we will be living for many thousands of years to come. We do not know much about the interior of our planet, especially about its deeper parts. Look at the deepest well which has been drilled. Indeed, very little compared with the radius of the Earth. We also get information from rocks which are carried to the surface of the Earth by ascending magmas. All remaining information is indirect, provided for instance by seismic waves traveling through the Earth and by gravity or magnetism. We need a lot of theoretical and experimental work to integrate all this knowledge and understand and predict how the Earth works. Seismic waves are a great source of information, and we will make use of them in this course. We will use two types of waves. In P waves, also called pressure or primary waves, the direction of oscillation of rocks is parallel to that of the wave propagation. P waves are thus very efficient and fast. In S waves, particles oscillate perpendicular to the direction of wave transmission and are therefore slower and very sensitive to the degree of coupling between adjacent crystals. Rocks which are partly molten will have very low S wave velocities. We use physical properties to infer the first-order features of the Earth. Temperatures and densities increase with depth, but show a sharp increase around 3,000 kilometers depth. P waves increase from the surface to a depth of around 3,000 kilometers, decrease and then pick up again. She waves have a similar behavior but nearly disappear underneath 3,000 kilometers. Rocks between 3,000 and 5,000 kilometers must be in a partially liquid phase. The depth of 3,000 kilometers is a fundamental discontinuity in the Earth and forms the boundary between the core and the mantle. The two domains have different composition, physical properties, and behavior. The Earth core results from the primary segregation of the gases forming the Earth 4.5 billion years ago. It is formed by minerals very rich in heavy elements such as iron and nickel. It still releases heat, which forms a substantial part of the heat reaching the surface. Relative rotation between the inner and outer core generate the dipolar magnetic field of the Earth and the associated reversals. With the exception of its uppermost part, the domain above the core mantle boundary is called mantle. Nearly 3,000 kilometer rocks of fairly constant composition, substantially different from that of the core. Rocks forming the mantle are very homogeneous, composed of elements such as silicium and aluminium, and of minerals such as olivine and pyroxenes. The corresponding rocks are called peridotites. This results in densities, seismic velocities, and temperatures which gradually increase, moving downward from the surface of the Earth. What is the physical state of mantle rocks? In the plot you see two curves, the geothermal gradient and the temperatures at which mantle rocks melt. With the exception of a small interval around 100 and 200 kilometers, predicted temperatures are always lower than melting temperatures, indicating that most mantle rocks are in a solid state. Despite the fact that they are solid, mantle rocks can deform in a ductile manner, which means without breaking. Indeed, all solids, if given enough time, can deform and change their shape. See, for instance, how glaciers move for kilometers without breaking. Rocks of the Earth will also deform, and over millions of years can even flow without fracturing. Going back to the plot of seismic wave velocities, we see that at depths of 100 to 100 kilometers, values are lower than the underlying and overlying rocks. This is the low velocity zone, a major feature controlling Earth movements. The reason for the low velocity zone becomes clear plotting the melting temperature of mantle rocks and the geothermal gradient. In correspondence with the low velocity zones, temperatures are slightly higher than melting temperatures. which results in partial melting of the rock. It will not surprise you that when seismic waves want to propagate through these rocks, grains will partly move loose from each other, thereby causing a decrease in seismic velocity. The low velocity zone is called asthenosphere. The layer of rocks overlying the asthenosphere is called lithosphere. The asthenosphere is of great importance in geology as it forms a soft substratum on which the strong lithosphere floats and moves.